Hello there! In this video I'll use game theory to solve the Monty Hall problem. This puzzle originates from the game show Let's Make a Deal and is named after its original host, Monty Hall. It goes as follows. Suppose you are given the choice of 3 doors. A car and 2 goats are randomly hidden behind each of them. First you choose one of the doors. Then the host will randomly open one of the 2 others, but never the one containing the car. Then you are given 2 choices. You can either keep your original door or switch. At the end, the host reveals the contents behind each door, and if the one you've chosen contains the car, you win, and otherwise you lose. Now, the question is, when you are given the choice of switching, should you do it? Is there even an advantage in switching? Since there are only 2 doors, you may think that they have the same chance of hiding the car. But that's actually not the case, and here's why. Let's take a look at what happens when you switch and the host hides the car behind the first door. You can either choose door number 1, 2 or 3. In the first case, you lose, but you win in the second and in the third. You can see here that you win 2 times out of 3, but you should also consider the remaining cases, although you'll notice that they are symmetric, so you'll end up winning 2/3 of the time. It's important that you try it for yourself. If you do, you'll understand that the fact that the host knows where the car is essential. If he instead opened any door at random, he could eventually open the one containing the car, which would go against the rules. So, switching is better than keeping, but is it necessarily the best strategy? What if the optimal strategy was keeping with probability p and switching with probability 1 minus p? The expected value would be the following formula. By keeping with probability p, you win p times 1/3, and by switching with probability 1 minus p, you win 1 minus p times 2/3. By rearranging the formula, you'll get the following function. It is decreasing, so you maximize it by letting p be 0. That means that always switching maximizes how much you win on average. Now I have a similar yet different question. A problem that I always had with the Monty Hall problem is that in reality, the host will not necessarily make his choices randomly. So, what should you play if we modify the rules that determine the host's behavior? To find out, we are going to draw the game tree. First, the host has 3 options. Hide the car behind door number 1, 2 or 3. I'll draw a dotted line to indicate that you don't know behind which one it's hidden. Then, you have 3 options. Choose door number 1, 2 or 3. After you choose your door, the host will either have 1 or 2 choices. For instance, if the car is hidden behind door number 1 and you choose that same door, then he has a choice to open door number 2 or door number 3. If you choose door number 2, the host will have to open door number 3. And if you choose door number 3, he'll have to choose door number 2. You can make the same reasoning for the other actions. After that, it's your turn, and you can either keep or switch. The last thing you need to complete this game tree is the payoffs, which are the probabilities of winning. For that, consider the first branch of the tree. If you choose door number 1, you win by keeping, regardless of what the host does, so you lose if you switch. If you choose door number 2 or door number 3, you lose if you keep, so you win if you switch. You can make the same reasoning for the other payoffs. Now, in order to get the expected value, I gave names to the probabilities to which you and the host choose your actions. You get the following formula. This time, it isn't so straightforward to find out what you should play. Your goal is to maximize the probability of winning, but what does the host want? In this problem, his intentions aren't defined. Maybe he doesn't want you to win and wants to minimize the expected value. Maybe he wants you to win. Or maybe he has his own payoffs. So how should you play given that you don't know his behavior? In order to find out, we are going to use game theory, more specifically zero-sum game theory. In mathematics, a game is any activity in which you and other choice makers, called players, make choices that result into defined outcomes. Zero-sum games are games in which what one player wins is what other players lose. The philosophy of zero-sum games is that players should seek to safely gain as much from the game as possible, independently of how skillful their opponents are. With that in mind, it's possible to define a value called the value of the game, that tells how much you are guaranteed to win on average if both players play optimally. If you play optimally but your opponent doesn't, then you may win more than that value. This is stated by the Mmax theorem proved by John von Neumann in 1948 in the book Theory of Games and Economic Behavior, written by him and his friend Oscar Morgenstern. Going back to our problem, now we know that we should be looking for the player's optimal strategies as well as the value of the game. To do so, we first need to list each player's pure strategies. A pure strategy is a complete plan that tells the player how to act at any part of the game. For example, here are the host's pure strategies. The first number designates the door behind which he hides the car. The next one tells what he does after you select your door for the first time. It specifies the door he chooses if he has a choice. For example, let's take a look at the strategy 1-2. First, he chooses door number 1. Then, if you choose door number 1, he has two choices, so he chooses door number 2. If instead you choose door number 2, he has to open door number 3, because he doesn't have any other choice. Now, let's look at your pure strategies. The number indicates the door you choose. The first letter tells you what you do if he chooses the leftmost door, and the second what you do if he chooses the rightmost door. A K means that you keep, and an S that you switch. For example, 2KS means that you initially pick door number 2. If you are in that branch, you are going to switch, because between door number 1 and door number 3, the third is on the right. But if you are in that part of the tree, you keep, because door number 1 is on the left. Now that we have both players' pure strategies, we are going to create the game matrix. Inside of it, we are going to set the payoffs. You can find them by seeing what happens when you put one strategy against the other. 1kk versus 1-2 gives 1. 1kk versus 1-3 gives 1. And then you go on, you get 0, 0, 0, 0, and the rest can be found in the same way. With this matrix, we are almost done. First, I want you to only focus on these rows. Remark that the payoffs at the strategy 1SS are higher or equal to the others. This means that if you play 1SS instead of the others, you are guaranteed to win at least the same amount. Such a strategy is set to dominate the others. The others are called dominated strategies, and you can eliminate them from the matrix. If now you focus on the following strategies, you see that 2SS dominates the others, and if you look at those, 3SS also dominates. You can already observe that you are left only with strategies that tell you to always switch. Therefore, I am going to rename them as choosing a door and then switching. Next thing you can see is that strategies 1-2 and 1-3, 2-1 and 2-3, and 3-1 and 3-2 are the same, so if the host has a choice, it doesn't matter what door he opens. Therefore, I reduced this matrix once again and renamed his strategies as hiding the car behind door 1, 2 or 3, and then doing anything he wants. With the game matrix as it is now, you will no longer manage to find dominated strategies. This means that the optimal strategies are mixed strategies. A mixed strategy is one where the player plays each of his pure strategies with a certain probability. There are many methods to find the mixed strategies. The one I decided to present takes advantage of the symmetry of the matrix. When permuting the columns, notice that the rows are also permuted. That remains true if you do any permutation of the columns. Whenever that happens, it means that there exists an optimal strategy that consists of playing each of the pure strategies with the same probability. This is called the principle of invariance. For this specific game, it turns out that this optimal strategy is unique. The only thing that remains to be done is to find the value of the game. It is given by the sum of the product of each payoff and the probability that its corresponding pure strategies are played, which gives 2/3. And that's it! By solving a more general problem, we've managed to solve the original puzzle, since it turns out that the optimal strategies are the host's behavior. And this is where I take my leave. May the cube be with you, and see you next time. Hello there!